Hi, Algebra 2. Today we're going to work on solving radical equations. So in this unit so far, we've learned how to simplify radicals. We've learned how to add and subtract radicals. We've learned how to multiply and divide radicals, including simplifying them by rationalizing the denominator. We've learned how to operate when we have a radical inside of a binomial. So we've done almost everything that we're going to do with radicals, at least this first half of the unit, except for solving equations that involve radicals. So that's our plan for today. So the first thing I want to do is go ahead and define a radical equation. And it is exactly what it sounds like. It's an equation that contains a variable inside of a radical. And so what this means is we have a particular situation that we have to identify our inverse operation and be able to use that to solve equations. No different than we have any other kind of equation that we've learned how to solve dating back to middle school. And so what it turns out is that squaring and taking the square root are inverse operations. In fact, you remember that from solving some simple quadratics. Right? So now this is the flip of that. We're going to square to undo square rooting. And so technically, because we now know that there's radicals other than square roots, we have cube roots and so forth, we're going to say that these equations can be solved by raising both sides of the equation to a power. So if it's a square root, we're going to raise it to the second power, square it. If it's a cube root, we'll raise it to the third, and so forth. So this is just a quick breakdown on the process. Okay? So our first move always is to isolate the radical. We can't do anything with any of the terms of the expression in the radicand until we've removed the radical. And so we need to isolate the radical first. So anything that's added, subtracted, multiplied, divided outside the radical, we're going to undo that. So in our example, we have a fairly simple example. Cube root of x minus 2 equals 0. So we're going to add 2 to both sides and get cube root of x equals 2. Second step, we're going to raise both sides of the equation to whatever root we have. So in this case, it's a third root. So we're going to cube both sides of the equation, raised to the third power. So cubing will undo our cube root. And then on the right-hand side, 2 to the third power gives us 8. So this works out to be x equals 8. So I'd like to walk through this example, and if you didn't get a chance to write this down in the notes in class, you can pause the video and write this down now. Or maybe you wrote it down in class and you want to kind of quiz yourself. Like, can you still answer this without looking at your notes? That's not a bad idea to do either. So here's an example. 2 times the square root of the quantity x plus 1 equals 14. So our first move is to isolate the radical. It's been multiplied by 2, so we're going to divide by 2 on both sides. So 2 divided by 2 equals 1. And so on the left-hand side, I just have the square root of x plus 1. The right-hand side, 14 divided by 2 is going to give me 7. So the square root of x plus 1 equals 7. So excellent. We've isolated our radical. We can't do anything with that plus 1 inside the radical, though, until after I've removed the radical. So I know a lot of us are looking at this and going, oh, subtract 1, subtract 1. We can't do that yet. So how are we going to remove the radical? Well, we're going to use an inverse operation. Taking the square root, what's our inverse? Squaring. So we're going to square both sides of this equation. So the left-hand side, the squaring and the square root undo each other, and I'm going to be left with just x plus 1, the radicand. And square the right side as well. So 7 squared, that's going to give me 49. So x plus 1 equals 49. And from here, it's a pretty straightforward one-step equation. So we're going to subtract 1 from both sides, and x equals 48. Okay? One of the great things about solving equations, and you know this dating back to your middle school days, is you can always know 100% sure that you're correct. You take that x value, put it back into the equation, and then simplify, and it should make a true statement. So if I replace x with 48, 48 plus 1, the radical is a grouping symbol, just like parentheses. So in order of operations, it gets done first. So 48 plus 1 is 49. Now I take the square root of that. That's 7. 7 times 2 gives me 14, so this equation checks out. All right, so let's have you try one on your own. So we're trying to solve this equation. 6 times the square root of x plus 10 equals 42. So you can go ahead and pause the video and try and work this one out on your own, and then we'll go ahead and check the answer. All right, so go ahead and check your work against mine. So the first thing we're going to do is I need to isolate this radical. So I'm going to divide both sides by 6. 6 divided by 6 is 1. So on the left-hand side, I'm going to have just x plus 10. On this side, 6 divided by 6 is 1. 42 divided by 6 is 7. So I have x plus 10. The square root of x plus 10 is equal to 7. Now I can go to work on removing this root. I'm going to do that by squaring both sides. So x plus 10, the quantity squared, square root of x plus 10 squared, I'm going to be left with just the radicand, x plus 10. Right-hand side, 7 squared is 49. So you should have x equals 39 as your solution. So one more that we can try. And again, you can go ahead and pause the video, work through this one on your own, and then start the video and check your work against mine. Okay, so let's see how you did. So this time through, we have radicals on both sides of the equation. And again, we're thinking, where have I seen this before? I've done variables on both sides, and I know I need to subtract one or the other. But look what's going on here. When I add or subtract radicals, I need to have the same radical part. Here I have square root of 8x plus 6. Here I have a square root of x, and it's multiplied by 3. So I can't just subtract square root of x here. That's not going to help me. And even if I divide both sides by 3, that's not going to get me any closer. I've got radicals on both sides. So I'm going to square both sides, and that's going to remove both radicals. So on the left-hand side, square root and squaring undo each other. I have just the radicand. Step lightly on the right side, though. Look what you have here, 3 times the square root of x. You have a product raised to a power. So remember what happens, and that power applies to both factors. So this exponent 2 goes on the 3. 3 squared is 9, and it goes on square root of x, which is going to give me just x. So kind of a little bit of a stumbling block there in this problem. You want to be very careful to not miss squaring the 3. All right, so now I have variables on both sides, and now I can solve this the way that we've learned long ago. And I get x is equal to 6. How do I know this is right? Well, let's go ahead and do our check. 8 times 6 plus 6, so take that square root, equals 3 times square root of x. Okay, so 8 times 6 is 48 plus 6. So that's square root of 54 equals 3 times the square root of x. Well, I don't know, does it? So let's go ahead and simplify square root 54 and see what happens. So we're looking for 2 factors of 54, one of them being a perfect square. And so we recognize that 54 can be expressed as 9 times 6. Each one of those factors can now get its own individual radical sign. So square root 9 times square root 6. Why would I want to do that? This looks like more work. Square root of 54 is a perfectly fine expression, right? No, because I can't leave a perfect square factor under the radical. So when I get to square root of 9, awesome, I can simplify that to 3. So 3 times the square root of 6. So it turns out that yes, 54 is equal to 3 times the square root of 6. And our work checks. So one more thing. Now that we're feeling pretty good about squaring both sides and then solving the resulting equation, we find out that there's one more step that we have to keep an eye out for. Okay? We need to check for what are called extraneous solutions. Okay? This kind of odd-sounding word that shows up in math. What do they mean, extraneous solutions? So when we squared both sides, we created kind of a new equation. And not always, but sometimes, when we create that new equation, there'll be values for x that solve that equation that do not solve our original equation. How do we know? We have to go back and actually check our answers to see if they work or not. So let's walk through this process. Square root of x plus 18 equals x minus 2. So we recognize by now that we need to square both sides. So squaring a square root, I get my radicand, x plus 18. On the right-hand side, though, x minus 2 squared, that's x minus 2 times x minus 2, right? I have to go and multiply this out, these two binomials. And so when I do that, I get x squared minus 4x plus 4. Here's your giveaway. You recognize this as a quadratic. So now we're thinking about, how do I solve quadratics? Well, there's some very simple cases I can take the square root of both sides, but that's how I ended up here. I squared both sides, so that's not going to help me. Sometimes we can factor and use the zero product property. If we hate ourselves and hate our lives, we can complete the square. Or we know that the quadratic formula will solve any quadratic equation. About 95% of the time when we're trying to figure out how to solve a quadratic, we want 0 on one side of the equal sign. I've already got my x squared over here, so let's make this side 0. Let's subtract x from both sides. Let's subtract 18 from both sides. So x minus x is 0. 18 minus 18 is 0. So good, my left-hand side is 0 now. On the right-hand side, x squared, negative 4, negative 1, that's negative 5x. And 4 minus 18 is going to give me negative 14. All right, can I factor this side? 2 factors of 14 that have a difference of 5. That's 7 and 2. This is negative, so the bigger number gets the negative. Okay, zero product property. Let's solve. All right, so we get x equals 7 or x equals negative 2, and you're feeling pretty good now, right? You've done this work. There were a lot of steps. You hung with it. You persisted in solving this problem, and you feel like I'm done. This is a case where, if you remember solving quadratic word problems, sometimes we would solve the equation, but not both of these would make sense in our problem. One of them would lead to negative time or negative distance. Your teacher would say, ignore that one. Kind of the same situation here. So we have to test both of these back in the original equation. So let's do that. So 7 plus 18 square root equals, questioning, 7 minus 2. So let's see, square root 25 equal to 5. And that's true. The square root of 5 is 5. Awesome. Let's try this one. Negative 2 plus 18, square root that, asking if that's equal to negative 2 minus 2. So square root 16 is going to be 4, which is not equal to negative 4. So what that tells us is we can ignore this solution, x equals negative 2. Okay? It is an extraneous solution. And I want to go ahead and take a look at a visual on that so we can see why that is. So let's jump over to Desmos real quick. And let's go ahead and graph y equals square root x plus 18, y equals x minus 2. So here I could see that these two curves intersect at 7, 5. So I could see at x equals 7 that they're equal, right? So that tells me that the solution x equals 7 makes sense. But over here at x equals negative 2, these lines do not intersect here. So that's a visual on my extraneous solution. So what's going on here? Well, we've got a radical function, which we're going to deal with a little bit later on in this unit. And you can see something kind of strange about it. It comes to the x-axis, y equals 0, and then it just stops. Negative y's don't make any sense in this particular type of function. So our range is limited to y is greater than or equal to 0. You can kind of see that if this was a parabola turned on its side and continues, it probably would hit this curve at x equals negative 2. But because that part of the curve doesn't exist, it's an extraneous solution. That shows us the whole idea of an extraneous solution. It was created by this new equation that we made rather than the original equation. All right, so good work here. I'm going to put a link to the homework version, quote unquote, air quotes, version of